Assalamualaikum and good day. We continue our lectures on the second order system. We have learned about the various response of the second order system, but now we want to focus on the underdamped response of the second order system. We have a few characteristics of the system. For the underdamped, we have peak time, we have which the peak time is actually the time required to reach the first or maximum peak. So this is the peak of the response. So the peak time is actually from the origin to the time it takes to reach the peak value of the plot here. And then we have the settling time. The settling time is actually the time required for the transient damped oscillation to reach and stays within plus minus 2% or 5% of the steady state value. So as I mentioned before, the settling time is when we have a plot here. So for example here, it starts from the origin and goes to the transient response until it reaches the peak, and then it will oscillate. And after some time, it will reach the oscillation, which will vary between these two border lines here, 0.98 and 1.02, which is actually plus minus 2% of the final value. When the oscillations reach within these two boundaries of plus minus 2% of steady state values, then we say that the system has reached the settling time. Next one is the percentage overshoot, which is the amount that the waveform overshoots the steady state or final value. So the percentage overshoot, we can find it by value at the peak here minus the value of the steady state here. So actually we can find the difference between the peak and the final value and multiply by 100%, and where we will get the percentage overshoot. And then we have delay time. The delay time is actually the time required to produce 50% of the final value. Let's say the final value is 1. The TD, the delay time, is the time taken to reach half value of the steady state error. Okay, so it is the time from this position, the origin, to 50% value of the steady state value. And then we have the rise time. So the definition of rise time is actually the same as that we have defined in the first order system, which is the time required to reach 10%, from 10% to 90% of the final value. So you can get PR over here from 10% to 90% of the final value. We have the peak time, we have zeta, we have settling time, and settling time is given by two different formula. That is, this is for the 2% settling time, and then the other one is for 5% settling time. So the settling time can be calculated only for those zeta, that is the value is between 0 and 1, because when zeta is equals to 1, there is no 2% settling time, because the response reach from transient response to steady state value without having the oscillation. This is for zeta equals to 1 and zeta greater than 1. Okay, critically damped and overdamped system. Given the value of overshoot, you can calculate zeta, as well as if you have been given the value of zeta, you can calculate the percentage overshoot, because these two formula is a function of zeta and pi only. So again, this is maximum overshoot, which is the peak here minus the final value, steady state value, and you multiply by 100 and you will get the maximum percentage of overshoot of the system. Next one is again we have this formula to find the poles location of the system, where we have a negative sigma d plus minus j omega d. So this j omega d is actually the damped frequency of oscillation. We can represent the settling time and peak time in terms of sigma d and omega d. Sigma d is actually the real part of the pole, So this is the exponential damping frequency, and the omega d here is imaginary part of the pole, and this is actually the damped frequency of oscillation. So we refer to this as plane again. So this is the j omega g, and this is the sigma d. So the sigma d is actually located on the real axis, and j omega d at the j omega axis over here. What we have next is we have these values of the percentage overshoot. For figure A here, we have the omega n, the distance of the pole's location from the origin. Figure B here is actually the value of zeta. If we have poles that is located on this line, along this line, the value of zeta is the same for these poles. As well as if we have poles that is located along the path of the omega n here, the value of omega n is constant. What's different is only the zeta, because depending on the omega n1 is the same. It's the same because it is have the same radius. Actually, when we look at this TP formula, TP equals to pi over omega d, we can see here the peak time is actually only related to the omega d. This is j omega d here. So we can say that when we have our poles that is located along the ray of the omega d here, so let's say this is omega d1, we can say when we have poles along this line, we can say all the poles at this line have the same peak time. As well as when we see that if we have these poles along this ray line here, we can say that the system for all poles has the same percentage overshoot. And if we have poles that is located along these lines, we can say that all the poles here will have the same settling time. So from here we can see that when zeta is high, the percentage overshoot will be reduced. So it is inversely proportional. Zeta and percentage overshoot is inversely proportional to each other. Alright, so and peak time will be reduced. So when we have percentage overshoot that is reduced, the peak time also will be reduced. This is the relationship between the percentage overshoot and zeta. As you can remember from the last lecture, we have this plot over here. So relationship between the zeta and percentage overshoot. Okay, so you can see here when we have a small value of zeta. So let's say we have zeta 0.1. So the value of zeta is very small, 0.1. So you can see the percentage overshoot for this is very large. So we can compare zeta that is greater in the value. So for example, if we take 0.4 over here, so the percentage overshoot becomes smaller as compared to zeta 0.1 here. Again, this is for the TS settling time. It is only related to the value of sigma d. So when sigma d is constant, means it stays the same, okay, on this direction, vertical direction. This settling time will be the same. Why? Because remember we have for the oscillation, that is zeta between 0 and 1, we have a real component and we have imaginary component. So like I have explained before, the real component actually it has this envelope, will be enveloping the value of imaginary part. So when we have the same envelope, that is the oscillation of frequency will be limit by this envelope. So what we have is actually we have the same settling time. What's different is only the frequency. Frequency is how it oscillates within its envelope, whether it is faster or it is slower. Then next, for the figure B here, we have the TP, peak time. Okay, the peak time is only related to the value of omega d. Means that if we have poles along this omega d becomes constant because it stays on the horizontal axis. Is what we have the same peak time. What's different is only the value of percentage overshoot, because it will either large or small, but it will reach the same peak time. Next is the constant damping ratio as shown in figure C. When we have the damping ratio, okay, we have this line, and if we have the poles that is located along this line, we have the same overshoot because it is related to the cos theta, which is equal to zeta. Remember, cos theta equals to zeta, we can see from this here, the same angle theta here. So what we have is actually we have cos theta equals to zeta, negative zeta omega n over omega n, which equals to negative zeta. So we have the same zeta value. Thus, what we actually have is we have the same overshoot. Okay, zeta define the overshoot. If say zeta is 0.5, we have 30% overshoot. Then we have for different pole on this zeta line here, it will have the same 30% overshoot. So this is the examples. If we have zeta 0.2 for omega n equals to 1 and omega n equals to 10. Although the value of omega n is different, 1 and 10, you can see here overshoot is the same for both omega n equals to 1 and omega n equals to 10. So in this case, if we make the omega n constant equals to 5 and we have different value of zeta, we have 0.7 and we have zeta equals to 1, we can see the difference in the overshoot. Okay, where zeta equals to 1, we do not have any overshoot, and we have slight overshoot for zeta 0.7. And for this case, we make the omega n constant and we vary the value of zeta. We have the difference overshoot. So in this case, actually, you can refer to this plot. We say that we have a value of the same omega n. Means the location of omega n is the same. We have the same radius over here, but we have different angle. When we have different angle, means that we have different value of zeta. Okay, so when we have different value of zeta, we will have different oscillation, different percentage overshoot for this each plot. Next is we have delay time and rise time. So the delay time is given by these two equations, where we have the first order approximation, and this is the second order approximation, the second order, and then this is the first order. This is the actual plot. So you can see here, if we compare first order approximation to the second order approximation, the second order approximation is much accurate as compared to the first order approximation. And we have the rise time, as similar to the delay time. We have rise time for the first order approximation, and we have for the second order approximation. Again, this is the actual value of the plot, and then this is the first order approximation. You can see here the first order approximation is quite off from the actual value of the plot. However, if we look at the second order approximation, we have this plot which actually about the same as the actual plot of the omega n TR here. So we can say that the second order approximation of the rise time is much more accurate as compared to the first order approximation.